In section 5.4, we're talking about common and natural logarithmic functions. Before we start, we're going to attempt to understand the relationship between exponential and logarithmic functions. So let's consider the function 10 raised to the x power here, and then also the function log of x. If we graph the two of those, then we can begin to understand what's going on there. Here I have a graph, and I have both of my equations graphed. I have 10 to the x, and 10 to the x is going to be the one lying on the top side of my line y equals x, and then I have the log of x also there. If I take off my axes, then you might be able to see these a little better. And let's look at a graph now. And I'm going to zoom 6 right now. So there's the first one. That's 10 to the x, and then here's the second one, log of x. All right, now you can see it looks like, let's take a picture of this here. Okay, so in this graph right here, it looks like one of the two doesn't continue, but it does. It's just that your calculator doesn't exactly show you what's going on. So these both continue here. So this one being 10 raised to the x power. You should notice here that it looks like they are reflections of each other over the line y equals x. And if that's the case, then they are inverses of each other. That's what inverses are. So what do we know about these? We know that 10 to the x and log of x are inverse functions. Further, we know that if the log of v is equal to u, then 10 to the u is equal to v. So let's look a little closer at that. So we have log of v is equal to u. Now, what you don't see when I write log is that this base here is 10, okay? So that statement can be transformed into an equivalent exponential expression or exponential equation function, which would be 10, that 10 base, raised to that u power equal to that v, okay? So those are going to be equivalent equations, and anytime you have a logarithmic equation, you're going to have an equivalent exponential equation. So here we have a couple examples, and we're going to take these logarithmic equations and write them in exponential form. So remember, as I said in the last one, you have a 10 here that you don't see. It's a base 10. If it's not given, it's a 10. So we would say 10 raised to the 1.4624 is equal to, and it's actually going to be approximately 29. Now, if you just plug that quickly into your calculator, 10 raised to the 1.4624, check that and make sure you get approximately 29 there. And then in the second one, also 10 raised to the 2.5775 power is going to be equal to the 378. So 10 raised to the, and again, check this in your calculator. It's going to be approximately, and it's just because it's decimals, and it's because something was rounded, and that's why it's approximately. Of course, if we're working with whole numbers, then it would just be that it was equal. Okay, let's evaluate each of these, and we're going to try to do it without using the calculator, with the exception of the last problem. So you notice what you have in an expression, and I want to know what the log of 100,000 is. Well, I know that I have a 10 here, and I don't know what it's equal to, so I'm going to write it as x. And if I have that and I don't want to use the calculator, then what I can do is I can say that 10 base I have raised to that green x is equal to 100,000. So if that's the case, then I know that x has to be equal to 5. I have 5 zeros there. So that's number 1. Okay. And in the second one, again, what I have here is that it's going to be equal to x. So I can write that as my base of 10 that I have raised to the x is equal to 10. If that's the case, I know that x is equal to 1. All right, and then in the next one, let's set it equal to x. And then I have, again, a 10 down here. So I can write 10 raised to the x power is equal to the cubed root of 10. Now this one's going to take a little more work, not too much more. But I can rewrite that cube root of 10 as 10 to the 1/3 power. And if I have the same bases, then I know that my exponents have to be the same since they're equivalent. So x is equal to 1/3 there. All right. And now on our fourth one, set it equal to x again. And on number 4, 10 raised to the x, again, is equal to -7. Okay, so first of all, when are we going to raise 10 to some power and get -7? Or 10, a positive number raised to any power, whether it be positive or negative or 0, and get a negative? It's not going to happen. This one is undefined. Okay. And then number 5. And number 5, we would have 10 raised to the 5th power is equal to x. And in this case, when we're trying to find x, 10 to the 5th is going to give me 10,000. And in the 6th one, we actually need to do a little work on our calculator. So we've got 10 raised to the x is equal to 52. We're not sure what that's going to give us. So let's rewrite that in logarithmic form. So log, the base would be 10, so I don't need to write the 10, of 52 is equal to x. Now I can plug this log of 52 into my calculator. Let's do that really quick. And do the log of 52. And I get 1.716. Okay. So then I can say here that x is approximately 1.716. Okay. And that's it for those. Now let's go and look at the natural logarithms. So natural logarithms, instead of having 10 to the x, now we're going to have e to the x and the natural log of x. So again, we can look at graphs of those to understand the relationships. And let's see if I can hear the graphs, or here are my equations. Let's turn those on. Okay, and look at a graph. And you're going to notice that, again, it looks like the two are reflections of each other over the line y equals x, and that's because they're inverses. And again, that natural log of x is going to continue even though it looks like it doesn't. It's just that it's getting really, really close to the y-axis as x gets closer and closer to 0. So, so your calculator just won't graph that part of it. So what do we know? We know that f of x is equal to e to the x and g of x equal to the natural log of x are inverse functions. And again, like I said in the last one, the natural log of v is equal to u if and only if e to the u is equal to v. So again, let's take a closer look at that statement. The natural log of v equal to u, that has a base of e. So essentially what this is the log base e of v is equal to u. So it's a logarithm with a base of e here. Okay, so that means that this can now be written as e to the u is equal to v. All right, which is what I have here. All right, and of course, every statement about natural logarithms is equivalent to a statement about exponents, and that is an exponential equation having a base of e. So let's look at these examples, and we're going to write them in exponential form. Remember that the base here is e, so I can say e raised to the 2.6391 is equal to 14. And you can put e raised to the 2.6391 in your calculator really quick and see if it gives you approximately 14. And then on the second one here, I would have e raised to the negative 1.6094 is equal to 0.2. And those are in exponential form. And we're just going to go through and use your calculator to evaluate each of these. So I have the natural log of 1.3, and let's just do those quickly in our calculator to make sure you know how to do these. So in the first one, I have the natural log of 1.3. So my natural log is just this key here, natural log of 1.3. Close my parenthesis. It actually doesn't matter in this case whether or not you close the parenthesis, but that's going to give me 0.26 there. And then we have the natural log of 203. And there we get 5.31, approximately 5.31. And then the last one, we have the natural log of negative 12. Okay. And watch what happens here. It says that it's a non-real answer. Okay, so in this one, what you would tell me is that it's undefined for the real numbers. So for number 3, it would be undefined for the real numbers. And you're going to see why in just a few minutes, why that's the case when we talk about the domain and the range. Okay, so we're going to look at a few more equations here. Let's say I have the natural log of x is equal to 2. And I want you to solve it by writing an equivalent expression. So the natural log of x is equal to 2. Well, I can rewrite that as e raised to the, e to the second is equal to x. And then in that case, I need to plug e squared into my calculator, and that's going to give me that x is approximately all right. And in the second one, the equation to start out with is e to the x is equal to 8. And I'm going to write an equivalent expression here. So this time I have an exponential, and I want to write it as a logarithmic. So the natural log of 8 is equal to x. And if that's the case, then I can just plug the natural log of 8 into my calculator. I'm going to find out that x is approximately 2.08. Okay, so that's about it for that section, other than the domain stuff that we need to talk about. So here we have a chart that we're going to work on. Let's go and look at the functions real quick. So this is an example. So what I have here is a graph of e to the x and a graph of the natural log of e, which you're going to see is actually going to continue here, and then you can see the line y equals x. So this here actually never crosses that y-axis. It actually never even touches it. It just gets really close to it. So let's work with e to the x here first. What would the domain of e to the x be? The domain, well, it goes forever to the left and forever to the right. So it looks like that the domain of e to the x is going to be all real numbers. Okay, and that's also the case for 10 to the x, and these should be exponents here. That should be 10 raised to the x, and this should be e raised to the x. So the domain is going to be all real numbers. Okay. Now, when we look at the range, what is the range going to be? Well, our range, it looks like our range starts maybe here and then goes up. Okay, it never goes below the x-axis. So in that case, looks like the range is going to be all positive reals. To get a better idea, you could also go and look at the table, and if you look at the table, you'll notice that your y value actually never touches 0, it just gets really, really close to 0. So it's going to be all positive real numbers for that. Okay, so key is positive here. Now what happens when you have inverse functions? When you have inverse functions, it's a reflection over the line y equals x, which means that there's an exchange of your x and y values there. So what should happen is that this is going to be here, and then this is going to be here. And let's see if that's the case, if we can look at the graph and tell that that's the case. All right, so if we're looking at here at the natural log of e, what is our domain going to be? So our domain looks like it's going to go this direction, okay, from 0 to positive infinity. So that's all positive real numbers. And what's our range going to be? Well, our range is going to constantly increase here. It's constantly going up at this end. And then here it constantly goes down. It's just going to get smaller and smaller and smaller as those x values get closer and closer to 0, infinitely closer to 0. So that means that our range is going to be all real numbers. Okay, so it is the case, and we can see it on the graph. So we've got all positive real here, and then here we have all real numbers. Okay. And that's all I have for section 5.4.